Hello friends, let's design today an integrator circuit, then build the circuit and then let us simulate that. So before starting with actual designing and building the circuit, what an integrator is. Integrator is a circuit. Here we will be designing it with an operational amplifier that integrates the input signal. So if I call this as an input voltage signal and we are measuring here the output voltage, then output voltage becomes the integration of the input voltage and it will be scaled by a parameter 1 by RC. As the operational amplifier is used in inverting operational amplifier mode, so the negative sign appears here. So for an example, if we take a step input signal, so for step input signal its integration will be, so it is nothing but it goes integrating at every instant of a time. So over the time it integrates. So it goes on accumulating and it should be a positive ramp. But as it is in inverting amplifier mode, so it is with the negative ramp. So for a step input, integration will be a negative ramp. Similarly, if we take the integration of a sine wave, we will be getting the cos function and that too with the negative sign. So minus of cos function. Now magnitude of the gain. Who decides the gain? So gain of this integrator is decided by three parameters actually. So magnitude is shown here. Magnitude of the gain is given by 1 upon 2 pi f RC. So frequency of the input signal, then resistance value. So which resistance? This resistance is this resistance that appears at the input side, this resistor and the capacitor, R and C elements. So this also decides the magnitude of the integration function. By what parameter it is scaled. So here it's actually inversely proportional to the R and C values. We'll be seeing this in the simulation part. Increasing and decreasing R, C values or the frequency values, how it affects the gain parameter. But a ideal integrator, that is with R and C, it has some limitations. What limitations are? So for an ideal integrator with R and C elements only, it would have the very small bandwidth and it is able to integrate the signals over the of very small frequency range. So here one resistor, if it is connected in parallel to the capacitor, then it becomes designing of a practical integrator. So practical integrator also has one limitation that at very low frequencies this capacitor would behave like an open circuit. So when the capacitor behaves like an open circuit and if no RF is connected, then the op-amp works in an open loop configuration. So open loop configuration, so even if there is no input applied, so offset voltage will exist and immediately the operational amplifier will go in saturation. So it will not be able to work as an integrator. This is also second limitations. So here if we connect the resistor RF in parallel to the C, then it becomes designing of a practical integrator that will overcome the limitations. Now in order to design an integrator, let us take one example. We want to design an integrator. Let us think it is able to amplify the operational amplifier is able to amplify and integrate the signal from the range of FA to FB. So if we take FA as a 200 Hz and let us choose a capacitor of value 0.1 microfarad, then design parameter is nothing but decide the value of R. How to decide the value of R and RF? So if we take FB 10 times that of a FA, then FB becomes, if we take FB of the 2 kHz, so let us design an integrator that is able to integrate the input signals within the range of 200 Hz to 2 kHz. So 2 kHz 10 multiplied by, so 2 kHz equal to 10 into 200 Hz. So let us design an integrator with the operational amplifier that will be able to integrate the signals within the range of 200 Hz to 2 kHz. So if we proceed ahead with the design and calculations, then RF should be of 8.2 K value and R should be with the value of 820 ohm. So with the calculations, whatever the value comes, but we should make it to the nearby standard value in which the resistor is available. So the design says that you should design an integrator with RF of 8.2 K, then resistance R in series with the signal source of 820 ohm and capacitor of the 0.1 microfarad. Now let us start designing the operational amplifier. We'll designing the integrator using the operational amplifier. So I will open the new window. So from the component part, I will go to the place analog IC. So as soon as you press the analog IC, so in the groups also you can go to the analog groups, and if nothing is typed here, just type here the 741 op amp. You can choose another op amp also. I will go with 741 op amp, which is familiar to us. So I will place the operational amplifier here. Now along with the op amp, we need the two resistors, one capacitor and the ground connections also. So I will complete the design. Okay, so I have selected the components, RF of 8.2K, then capacitor, let us call this capacitor simply C. So RF and C, and this resistor, this is a resistor R. Now in order to do the connections more conveniently, I want the inverting terminal at the upside, so I will just flip vertically. Okay, so now this is the pin number 2 with the inverting input terminal, non-inverting terminal 3 is to be grounded. So we know the circuit diagram. So expected circuit diagram is in the feedback part, we are connecting here the one capacitor, one resistor, and at the input side one resistor of 820 ohm. Let us do the connections and then do the connections of supply voltages also. So I will join these two resistors to the inverting input terminal. This is to be grounded. Non-inverting terminal again is to be grounded, and the feedback capacitor is to be connected between this point, the pin number 6, which is output pin number. You can go through the pin configuration or the pin number details of IC741. So inverting terminal, non-inverting terminal, output terminal 4 should be connected to the minus VEE. So I will again go to the sources. So from the sources I will call VEE. Okay, so V is to be connected here and VDD is to be connected to pin number 7. Again I will just flip it vertically. Need to change its value also. Let us make this of plus 12 and this to be of minus 12. Equal in magnitude, opposite in direction of op amp. Okay, fine. So this is what the connections are. So this is what we have designed the circuit within the formulas. Okay, before doing this ground connection, okay, so we'll remove this. We need to do the connection of a source, and then we'll be connecting here the CRO to observe the waveform. So I will choose the oscilloscope. So one channel of the oscilloscope is connected to the output terminal and the next terminal is to be grounded. So I can make the copy and then paste it here. So negative terminal is to be grounded, and I will connect the B channel to the input side. But before that we should do the connections of function generator. So I will choose the function generator to provide the input. So this we can do the ground connections. Negative is grounded and here the positive is connected here. So this is a function generator. So what specification should be given of the function generator is known to us. So let us choose the value of input signal parameters. So Vn should be, let us take it of the 50 millivolt peak to peak, and let us choose it of one frequency within the 200 Hz to 2 kHz, for which we have designed the circuit. So let us initially keep it as a sine wave only. So let us make this of, okay, 1000 Hz, and amplitude, peak to peak amplitude. So let us keep it as a 25 millivolts. Yes, 25 millivolt peak, so it would be 50 millivolts peak to peak value. So this is the details of the function generator. Now let us see if we can observe the waveforms on the, we'll connect with the positive terminal. So positive terminal is connected here and negative will be connecting it to the ground. So to identify and differentiate between input and output, I will change the color of this to the blue color. Apply and then OK. Let us see. Let's see now if we are able to get the waveforms on the CRO. So if I run the simulation, see, this is the waveforms. So if we are able to see the waveforms, see, we should know that input is in millivolts. So bring this scale into the millivolt range and adjust this to the appropriate value so that we will be able to observe the waveforms. Now if I change the amplitude levels, we can find the values. See, if I pause the simulation, so this is what the waveforms are. So if I go, so blue color is for the B channel. Channel B, make a note here, channel B is connected to the input and at the channel A we are getting the output waveform. So if I go to the positive peak of this, so from where the waveform starts, so this is the input waveform. So this is the sine waveform and this is a minus of cos function. So this is the input and output. Now we can observe the effect. What effect? Already we have seen, if we want to change the magnitude of the output waveform, that is possible by changing the value of R and C. So if I want to change its amplitude of the output waveform, by changing the values of capacitor and resistance, it is possible. But we'll come to this point later. Before that, now what happens if I do the input, that is a square waveform, which is in the form of a step input, increasing and decreasing. So positive and negative voltages. So what happens to the waveform? See, these are the waveforms. It will take some time to get it stable. So this is the waveform for, so the input waveform is blue color waveform and here we are getting the output in the form of a ramp. See, for the positive values, it should be a positive ramp, but exactly we are getting here the negative ramp. Now if I will try to enlarge it. See, so for the positive or plus VSAT value, positive values, we are getting the negative ramp, and for the negative values where we are having the stable output, constant output, we are getting the positive ramp. So here this particular waveform, which is a we cannot say step input, but for a square waveform with the 50% duty cycle, the waveform is turning into the combination of positive and negative ramp respectively with this particular durations. Now we can see the effect onto these output waveforms. What is the effect by changing the component values? Now what I will do initially, I will change the value of this capacitor. Now what should happen if I reduce the value of capacitor, the amplitude should increase. So instead of 0.1, if I make this as a 0.8, okay, instead of that, let us increase the value 0.15 microfarad. Earlier it was 0.1 microfarad. If I make it 0.15, increasing the value should decrease the amplitude. Now I will make this okay, and if we simulate, yes, amplitude has been reduced compared to the earlier output. So by increasing the value of capacitor, its amplitude, output waveform's amplitude. So output is red color waveform. So amplitude has been decreased. So see, gain is decided, magnitude of the gain is decided by the capacitor value. Similarly, same effect can be observed by changing the value of resistance. Instead of 820, if I make this 1200, again I am increasing the value of this resistance. Increasing the value of resistance, still should it decrease the magnitude of the output waveform. See, again the amplitude of the output integration has been reduced. So this is how the effect is there. Same effect can be observed by changing the frequency also. So what we have done right now, increasing and value of R and C is decreasing the magnitude of the gain. Now let us see what is the effect by decreasing the value. If I make this equal to 500 Hertz and if we simulate, let us see the effect onto the output waveforms. So decreasing the frequency has increased the amplitude. So this is what the magnitude of the gain is decided by the parameters which was given here, inversely proportional to the value of input frequency, capacitor value and the